All right. So are you guys all excited to be done with your data collection? Yes. It's a lot of work, isn't it?
Yes.
Does it give you?
Does it? Why?
We started at like at 3 o'clock. I started. But we finished.
This morning?
Oh no.
I was like, you're canceled.
It gives you an appreciation for how dirty the data is that gets used, I hope. Did anyone find that they had a state that was just wonderful and put it already in electronic form for them, and basically all they had to do is click like one button? And
Yes. No. Not one button.
no one button? No?
I had it somewhere it was like every different check for every different voting ballot for every different precinct was a separate line, so it was like 277,000 lines long per year.
Per year.
I didn't like look through it.
Okay. I was like, he can leave now.
All right. So I'm hoping, I'm not going to require it, so this is not something that you're going to have to do for credit for this semester, but I'm hoping since the election is on Tuesday, that you might be able to download very recent election information and be able to have up-to-date decisions that you suggest. Because I think based on the polls that are coming out, that we're going to have a different election this year than we had 2 years ago, and having different elections gives more variety to the model inputs that you get. So if you feel like your state is kind of samey year after year after year, this might be an opportunity to get a little bit less of that monochromatic view of the world, whether that's red or green, blue. Yeah. So we're going to start talking over the rest of the semester now how to use all the data that you've collected to start building some models about how you might build these congressional districts. Okay? We have some of the tools already in place from what we've done already in class to build your first initial model that's going to be due next week. Okay? So your initial model next week is going to be super simple comparatively. Because I'm going to let you break one of the fundamental rules that people who build these redistricting plans are not allowed to do, and that is to make discontiguous districts. So in other words, if this is your state, if you got the luck of the draw and you get to do Wyoming, right? And it was redistricted instead of having one representative for the entire state. With your solution, this will be a legal solution for next week. That this is a district right like this. That those 3 counties are part of District 1. Okay? That will be legal for what you turn in on Friday. That is not legal. It's not legal. Okay? But this will get you on the first step of building your model. Okay? And so what you're going to be required to do is you're going to be required to build your state districting plan such that you get the smallest difference between your largest district and your smallest district. Okay, so you want to have that. That is what your objective is going to be for Friday's turn-in next week. Yeah, Anna.
Difference in what?
Population. Okay, so what you already have how many people live in each one of your smaller voting districts. I'm going to call it counties because for almost everyone, that's what they are, but it's not exclusive, okay? So you can take your counties and you know how much people live in each one of those, and you can say, I'm going to make County 1 go into District 1. I'm going to, let me not use two numbers. County A goes into District 1, but County B is going to go into District 3, and County C goes into District 4, and so forth. And so what you're going to do is you're going to end up with an assignment where you have your counties right here. So 1, 2, 3, 4 are A, B, C, and D, right? And the congressional district that they're assigned to. So County A could be in 1, so could B, but maybe 3, 2, 4. This is the output that you need to turn in for Friday. And your objective function, like I said, is just going to be to minimize the difference between the largest sized county and the smallest sized county. The largest sized congressional district, population-wise, and the smallest sized district. Okay? So what does that sound like compared to some of the tools we've already used so far in class? Which problems or what problem or problems does that sound similar to? Everyone is either not sure or doesn't want to say the wrong answer. This could be similar to either the game theory problems that you did, right, where you tried to maximize gain or minimize loss, or it could be the investment allocation, where you tried to maximize your minimum gain. Okay, right? So what you can do is you know also the population for each district. So you can get the population for District 1, population for District 2, and so on for each of those congressional districts based on your assignment right here. So then you know what the difference is between these two. You know what the difference is between these two. You know what the difference is between all pairs of your congressional district, right? So you'll get that difference here. You'll get this difference here. You'll get this difference here. And then you're going to have some variable right here that you want this to go low, right? So it's going to be, your goal is going to be to minimize this value because you want to make it as small as possible. But what you're going to do is, compared to all these, you're going to set a constraint that it has to be larger or equal to all of those different differences. Okay? And as a result, this can only go down as far as the largest difference between any given congressional district is. All right? And so that will drive, so what are your variables going to be in this model right here?
The district number.
Yeah, these are your variables right here. That's what changes. You're going to let the model change those assignments to the different counties. You're going to put in these constraints right here, and then these populations. How do you compute these populations?
The sum of all the counties in the district?
Yes. So how you it turns out that if you use an equals if inside of a cell, that the solver cannot work with that because that's nonlinear. Okay? So, it gets a little bit more complicated than just assigning a 1, 2, 3, or 4 here. Okay? What instead you have to do is okay, and this is a 1 if you want it in A, and a 0 if you want it in there. So you're going to, instead of having one variable that assigns a district, you're going to have a row of 1s and 0s, right? So that these are actually your variables right here. Okay? Does this assignment make sense? We're not done. Yes, Seth.
So are we, for the redistricting, are we redistricting the counties and what districts they go in? Or
Yes.
are we smushing counties together?
Yes. Just like your current redistrict, you're ignoring what the current congressional districts look like. You're coming up with your own plan for what the districts should be.
So like as an example, like Indiana has 92 counties and how many districts, like 12 or 9 or something?
Mm-hmm.
So are we coming up with a new plan for 9 districts? Or are we coming up with are we combining counties together?
You're coming up with a new plan for those 9 districts.
Okay.
So on average, with that scenario where you say Indiana has 92 counties and 9 districts, if all the counties were uniformly populated, you would expect there to be 10 counties in each district, right? 9.2. So you would expect 9 of the counties to have a 1 in this column and the other 83 to have a 0.
But you want to do it by population.
Right. So since it's not uniformly populated, that's why you get these differences in here. Okay? Yes, Anna.
How do you get it to put in 1s and 0s?
They're variables. Okay? That's a good question. I want to show this inside of Open Solver here. That's not what I meant to do. No. You're going to add a new constraint. We'll get into more details after the test on Wednesday next week when we start doing Chapter 7. But I want you to start making progress now. So, if you see here on the screen, in addition to an equality less than equal or greater than equal, there are these other kind of constraints here. You will want to pick this bin that stands for binary. Okay? That means that the only legal value in that cell is a 0 or a 1. Okay? So you're going to put a giant set of constraints around all these values here that makes them binary. So you can only have 0s or 1s appear in any of these values right here. Yes?
So then you wouldn't have a value in the...
Correct. You would omit the second box right here because it would just say this first set of cells right here is binary. Okay, and that would restrict the values that Open Solver will put into this set of cells to 0s and 1s. So it will assign A to a district or it will not assign A to a district. What problem do you see if we stop there? Yes, it could assign if that's all we had is a binary, we could do this, right? And that's not legal with, well, for what you're doing, it's not going to work. You can only assign one of these voting districts, these counties, to one of your congressional districts here. So what do you need to do to keep it so that it stays right there? What do you have to do? Yeah, you need to make sure that this entire row right here equals 1, the sum. Right? Yes?
Is there a convenient way to do that so we don't have to put in all of the rows? Like, how do we make, we want all the rows to have that constraint?
Right. Well, you'll have a sum column right here, right? And then you can just highlight that column and set it equal to 1, right? Whatever that column is, you'll put in here, and you'll put the fixed value of 1 into here. Yeah. So it's a number of constraints, but it's one common type of constraint. So you won't have to highlight 100 different counties, each for their sum to be equal to 1, because you can do it in one operation. I thought I saw a hand. Yes.
So you said we're gonna learn about this after our test?
We're going to go into more details of what these binary constraints are and what these integer constraints are and how they work.
It's gonna be due on Friday.
Right. That's what I'm going over now, what you need to know in order to be able to do your model. So we'll go into more details in how these binary constraints work, how these integer constraints work. Because I have now given you enough so that you can do your model for Friday, but I haven't given you enough understanding how you could refine that model from Friday beyond for the requirements that you need for following weeks. And so that's what we're going to do in Chapter 7 and beyond. Yes?
So the goal is to have the smallest possible difference between the population, the highest district population and the lowest district population?
That is correct.
Or
The-
congressional district?
I'm going to repeat that to make sure everyone hears that, especially on the recording. The goal is that you find the smallest, so with this allocation, you can then compute what the population for each of these districts is, right? And now you can compute what the difference in population is for each one of these districts. And you want to minimize the largest difference between all those different combinations of districts. Okay, so this becomes a variable as well. Right, so let's see. I got onto this because I said you can't do an if here now. So how do we do? Let me erase this for a second. So you're going to have this District 1, District 2, District 3, and you're going to have population 1, 2, and 3. What is going to go into this box right here?
Some of it.
Yeah.
The sum of all the county populations in the district.
No, and I can see how you'd say that. That's going to end up down here. Okay? This is going to be how many people from County A are in District 1.
But it's either all of them or none of them, right?
Yes. So how are we going to do this? I'll put a population column right here. And what you're going to do is you're going to do,
Just multiply it.
yes, I heard it. You're going to multiply this number times this number right here. And that keeps it linear. So this is the District 1 value, which I'll make a pointer to. This is, oh, that didn't work. This District 1 value refers to this here, and we're multiplying it by County A's population. Right? So in this case, this is 1. 1 times this population is going to be the population, right? If we repeat this here, But now it's District 2 times that same population. We see that that's 0. 0 times that population is going to be 0. Right? So you're going to have this set of numbers here where you're going to have one population value and a bunch of zeros here. Right? Just like in here, you're going to have 1, 1 and a bunch of zeros. And the population numbers should mirror your 1s and zeros. They should look the identical shape and form as each other. And then we can then sum this entire column right here. And this value here is going to be the sum of all the counties that are in this district. The population sum of all the counties in that district. Now, down here, you're going to have all the populations for each of your congressional district assignments. And these are the values that you compute the differences of. Okay? And you could make this a grid where this is District 1, District 2, District 3, District 1, District 2, District 3. And these grid points right here are just the appropriate subtraction between these two values here, right? So this value right here is District 3 minus District 2. This value right here is District 1 minus District 1, which is going to be 0, right? And you can do that for all your districts. This grid right here gives you all of the differences between all of your districts. Right? And then you're going to have this value that I erased and now I'm putting back in here that we're minimizing. Right? And we want it to have what relation to all these values here? No, it can't be less than or equal to all of them because then we can make this super small, right? We can make it negative. Right? The constraint is that this has to be larger than or equal to all of these values. And that's how we're going to push all of these to be smaller because our goal is to minimize this. But it can only be as small as whatever the biggest difference is in here. Yeah, Nathan.
So you got one little rectangle in that square. Is that District 3 minus District 2? Or
Yes.
District 2 minus District 3?
Well,
Doesn't matter.
it doesn't matter as long as you're consistent throughout this whole grid, right?
Okay.
Yeah. Because you will do, if this is 3 minus 2, then this is 2 minus 3. Yeah, Josh.
Is there a reason you're using a full table for that and not just doing, like, making an objective function cell that's the maximum of the population of District 1 through 13?
Yes, because
minus
the
minimum?
function maximum is nonlinear.
Okay.
Pretty much all the functions inside of your Excel toolbox are nonlinear. All right, does this make sense where you're going from here? Okay? At this point, this is the first assignment you're going to use with OpenSolver that will not work with the built-in Excel solver. There are too many constraints. Okay? And I'm sorry, I know a lot of you, OpenSolver has broken on your Apple systems this semester. So that means you're going to have to go into the CSE computers and work on them there. That's what's going to happen, period. I apologize. I did not anticipate it breaking for you. But the alternative to use the Excel solver does not work. Okay? So, you're going to have a lot of constraints, right? You're going to have, let's say, let me just put in fictitious numbers here. Let's say you have 5 districts. Okay? And I know some of you have a lot more than 5 districts. Let's say you have 60 counties. That right there, that's 300 constraints. And constraints. Okay? Because you have a binary constraint for each one of these values right here. Okay? You also have another 25 constraints here. All right? And if you increase any one of these, it's just getting larger, right? That's far beyond the capacity that the Excel solver supports. And so that's the whole reason why I went to OpenSolver at the beginning of the semester, is to make sure that you'd be able to build these models without having to switch tools midstream. All right? Questions? Yes?
So what would be the formula inside the beginning box or bar?
There is no formula,
Okay.
right? It's just going to be a variable.
What is the OpenSolver constraint then?
That it has to be larger than every one of these values in here. Larger or equal to.
So
Yep.
will it end up being like just the biggest one though?
Yes, so
Okay.
it'll be the biggest difference, but because you've made it a minimized objective, sorry, it's going to, OpenSolver is going to do its best to push that down as small as possible. So it's going to come up with however it's going to distribute the counties, it's going to do that in such a way that the biggest county population, biggest congressional district population minus the smallest congressional district population is as minimum as possible. Okay? Does that make sense? How many of you have very large metropolitan areas that dominate a county? So you have a county with more than 1 million population. Okay, a couple of you. For those of you who do, I want you to slightly modify your model in the following way. Okay? Because we're not breaking up those counties into smaller units, which is what would have to be done in a normal redistricting effort. Because roughly 700,000 to 800,000 people are allocated for each representative in your state. So if you have more people in a county than should be rightfully assigned to a representative, I want you to just by fiat assign a certain number of representatives to that county and exclude that county from the rest of your model. Okay? So let's say, let me make this really easy for instance, let's say that you have a state with 10 million people and you have 10 representatives or 10 districts, same thing, assigned to your state. What you would say is, I expect there to be 1 representative per million people. Okay, and so you look at all your counties that have more than 1 million people in them and just say, oh, they get a representative, and then exclude them. Because otherwise, this model is going to kind of break, because you're going to have this giant county or giant 2 counties that it's going to be really hard to balance between. Okay, so you're just going to say, Those counties just get their representative, and we just break up the rest of our state into, so let's say there were 2 counties, each with 1 million people. In this example right here, we would assign 1 representative to each of those counties, and then we would break up the remaining 8 representatives among the remaining 8 million people in our populace right there.
Okay, so like in this, if county A had 1 million people and county B had 1 million people, you would set like
You would just hard code
1
1
and then a 1.
and then 0, 1.
And then you would just set the district 3 through whatever.
Yes. Okay, and you'll do that through the rest of the semester. Yes.
You want like at least 1 million people, right? There's like.
Well, figure out what the representation should be for your particular district, for your particular state, because every state has a different number of people assigned to its representatives. So if it ever goes above that number, then just hard code that in. All right? That only, just so you know, that only happens with very large states. You'll have plenty of other representatives to play with. All right. Go ahead and start working on this so that you can ask me questions about it Monday. Okay? And I would like you to give it an honest effort over the weekend so that you can ask me those questions on Monday, because Wednesday isn't available for questions, right? Because that's our next test. Okay? So you don't have to have it done, but at least get a good start on it. Make sure you've got your equations and got an idea of how you can translate from what I wrote on the board to in your Excel spreadsheet. Yeah. My hope is to finish. I want to finish talking about the redistribution problem that we started on Wednesday. Hopefully, I can finish that today. I have another problem type that I want to go over, which is an assignment problem, which you have an example, which is also due Monday. And then I'll leave it open for questions for the rest of the class period. Yes?
Is our test using computers?
No. You will not be using computers for the test. It will be very similar to your last test, where maybe you'll set up what the model is, so you know this equations, these are the demand equations, these are the supply equations. Using the sensitivity analysis like we did in chapters 4 and 5. So I might produce, this is the model, and here were the results, interpret it in some way. Is it valuable to add another, offer another airline seat or hotel room? If you could increase this investor's risk, what would the new objective be, and so forth. So you both have to be able to set up these models and interpret the results of those that have been run. All right. Okay, so let's go back then to the problem that we were looking at on Wednesday, which is in your book is 622. Remember, giving context here, this is where we have a car rental company, and they're at different locations. Some of them have extra cars, some of them do not have enough cars, and we want to, and this is where the name of the problem comes from, we want to redistribute our resources across these different locations. And we want to do that in such a way that it minimizes the overall expense of sending those cars from the over supplied locations to the applied locations. Okay? So we talked about our formulas on Wednesday, and that's then when we ran out of time. So let's see how that plays in our model on the screen. So in a normal system, these places would have names, right? But we've still got these numeric nodes. So I'm just going to put those in here as are in our diagram. So 1, 2, 3, 4, 5, 6, and 7. And there's two values that we need to keep track of, just like we have been for all of our transportation and transshipment, our network flow, maximum flow, shortest path, all of those, we've kept track of a cost and an amount that's traveling. So I will do costs first. So that's right here. And I will copy this and paste it down here, and this will be travel, movement, I don't know what to call that. Okay, and I'm going to fill this up first. So if there is not a connection, do we want it to be a high cost, or do we want it to be a low cost to allow the program to avoid the connection? We want it to be high cost. So I'm just going to fill this all with thousands to make it easy. And then I'm going to fill in the locations that have less. Okay, so we see that 1 to 2 costs 20. And notice, if you look at your problem, that these are not all bidirectional arrows. Right? 1 goes to 2, but for some reason we can't get back to 1 from 2. Okay? You can't change the arrows on this problem. You need to make sure that you preserve these directions. So 1 also goes to 5 at 25. And those are the 2 outgoing spots from 1. For 2, it goes to 7 at 45 and to 5 at 30. For 3, it goes to 1 at 20 and to 6 at 35. 4, where does 4 go? Goes to 2 at 30. Where does 5 go? It goes a bunch of places, right? 5 goes to 4, 15, 6, 28. Up. And 6, where does 6 go? Goes to 7, 12. And 7 goes to 4, 27. Did I get all of them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
5 goes to 3.
5 goes to 3, thank you. 25. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. Okay, I think I've got them all there now, right? So, what does this row represent again? What does that row represent? What's going out of? Out of 1. Okay.
2
So
goes to 7 as well.
2 goes to 7?
Yeah, 45.
I have that.
Oh, I was looking at the top one.
Thank you. So this is leaving. And we said that's the sum of those values right there. And what does this column represent again?
Everything going
Everything that's arriving at 4. So I'll just call that arriving. All right? There's one piece of data on our graph that we don't have in our spreadsheet yet, so we know we're not done. What's that one piece of data? What's on our graph that's not in our spreadsheet?
Like the surplus or the.
Yeah, our inventory, right? So let's go one by one. Node 1, what value is it? -8, so do we want more to arrive or do we want more to leave? More to arrive, so I will put an 8 here. Okay, how about 2? What's the value at 2?
5.
Okay, so do we want more to arrive or more to leave there?
You want -5?
Want more, -5 to, we want 5 to leave, right? Up to 5.
You want -5 to go back?
Okay, how about node 3? What's node 3?
+3.
Plus 3, so it belongs in the supply or the demand? Supply. How about node 4?
-3.
-3, so that belongs in supply or demand? It's demand. And notice I'm changing those from negative to positive because we don't have a negative demand for those. Thank you. Okay, node 5.
+2.
So that is in our supply, right? Node 6
-5.
and node 7.
+6.
Okay. So now we've got all the values from our diagram on the spreadsheet. So we now have a hope of building a model that will reflect what we're trying to do here. Let's go ahead and start trying to do that. All right, so our mod, yes.
Could you, kind of going back, explain why we put 1,000 instead of 0 and like what?
Yes. Okay, so why did we put 1,000 in these costs right here?
It's very expensive.
Yes, so we intentionally make it expensive because there's not really a connection, let me pick one right here, between location 3 going to location 4.
Mm-hmm.
So we don't want the model solver to assign movement between those two. So we pick such an expensive value there that it's just going to avoid that route that doesn't exist. So what we don't want to have happen is we don't want to have some value here for it to say, hey, move 5 cars from 3 to 4. That would break because we don't have that location. And so as a simplicity for building our model, we just write the cost of 1,000 here. If you, you could just model the different costs that exist, but then it takes more time to build that model, right? Because you wouldn't have the rectangular, and you'd have to enter each individual constraint into the open solver. And so this is just making it easier for us to build the model and let the computer do the hard work.
How does that differ from when would we put 0 in there instead?
We put a 0 when it was a maximum flow, and then that was a capacity and not a cost.
Okay.
And so in that case, we wanted to see how much could go through there. And so we didn't want them to stuff stuff through a channel that didn't exist.
Okay. Makes sense.
I did miss one thing here. What was that? Objective, which is? Total cost. How do we compute the total cost?
Some product
Some product of these costs per route with the amount of cars that are moving between any of those given locations right there, right? All right. So our objective cell is what we just put in, and we want to maximize or minimize that. Okay? What are our variable cells? They're this, right? How much cars do we move between any given location? And our constraints here. Let's do our first constraint for node 1. What should the constraint for node 1 be? So I heard this. The arriving should be greater than or equal to.
Can we make it just
Arriving is greater than or equal to this 8. And I'm going to say that's not quite right. What's wrong with that? No. What did we say could happen at location 1? Could we send more than 8 cars there? Yeah. Could we send cars away from 1? What need to be true in relationship between those two values?
We need to send out less.
Yeah, we need to have 8 more arrive than we send out, right? So we need to incorporate both the arriving and the sending. So we can't just compare these values right here, because that excludes the ones that we had leaving that, right?
So arrive minus demand is greater than equal to 0.
So arrive minus leaving.
Arrive minus leaving.
Right. So I'm going to do that net arrival right here is B20 minus I13. Right? That's how much we arrive is B20. Subtract off how many left. And that's the value that needs to be at least 8. So our net arrival has to be at least equal to our demand.
So it's
Okay? And we can do the same type of thing for these others. So I'm going to copy this here and here. And I'll do the same sort of constraints for nodes 4 and node 6. So the net arrival has to be larger than or equal to 3.
Could you do those all at once?
You can. I hate doing that control clicking thing, so
Okay.
I'm doing it separately. The net arrival is larger than or equal to 5. Okay? So that gets our demand nodes. Now, let's consider our supply nodes. All right? What needs to be true on node 2? Can we just compare these values right here? No, what do we have to do? We have to do the same thing like we did here with the net arrival. We need net loss here, right? And that's going to be I14 minus C20. Right? And what needs to be true about that value right there? Right, we can't lose more than 5, right? So that needs to be less than or equal to our supply. And we can do the same thing for these other. Whoops. So I'll do 3 more constraints here, and then I know time is run out. So this is less than or equal to this, and this is less than or equal to this, and then finally this is less than or equal to this. Oh, I didn't. Variable cells. How'd that happen? There we go. And so you can see that we sent them all, and now we have what we need for a cost of $81.97. If you look carefully, you will see that, for instance, we send 6 out of 7. We didn't send any extra through here, did we? All right. Have a good weekend, everyone. I'll see you on Monday.